Alcohols are organic molecules that contain one or more hydroxyl groups attached to a carbon atom or atoms as shown in the illustration. By contrast, phenols contain one or more hydroxyl groups attached to a carbon in an aromatic ring. In phenols, the carbon attached to the hydroxyl group is sp2 hybridized. Alcohols and phenols can be classified based on how many hydroxyl groups are present. Monohydric alcohols and phenols have one hydroxyl group. Dihydric alcohols and phenols have two hydroxyl groups, while trihydric alcohols and phenols have three hydroxyl groups. Monohydric alcohols can be classified on the basis of the nature of the carbon atom attached to the hydroxyl group. These carbons are either sp3 or sp2 hybridized. We will first consider hydroxyl groups attached to sp3 hybridized carbons. In a primary alcohol, the carbon attached to the hydroxyl group is linked to one other carbon-containing group or to none of the carbon-containing group, as shown in the illustration. In a secondary alcohol, the carbon to which the hydroxyl group is linked is attached to two carbon-containing groups. In a tertiary alcohol, the carbon linked to the hydroxyl group is bonded to three carbon-containing groups. An allylic carbon is a carbon atom bonded to a carbon-carbon double bond. Note that the allylic carbon is sp3 hybridized. An allylic alcohol has a hydroxyl group attached to an allylic carbon. Allylic alcohols can also be characterized as primary, secondary, or tertiary. As we saw before, a primary alcohol has one other carbon group attached to the allylic carbon. Secondary allylic alcohols have two carbon-containing groups joined to the allylic carbon. Tertiary allylic alcohols have three carbon groups bonded to the allylic carbon. A benzylic carbon has an sp3 hybridized carbon bonded to an aromatic ring. Thus, we can describe a benzylic alcohol as having a hydroxyl group attached to a benzylic carbon. The molecules illustrated here are examples of benzylic alcohols. Benzylic alcohols can also be classified as primary, secondary, or tertiary, depending on the number of carbon groups bonded to the benzylic carbon as shown. Here is a problem for you to try. Classify these alcohols as primary, secondary, or tertiary alcohols. Molecules A and B are both secondary alcohols. In both A and B, the carbon bonded to the hydroxyl group is attached to two other carbons. Molecules C and E are tertiary alcohols. The hydroxyl bonded carbon is bonded to three other carbons. Molecule D is a primary alcohol. Only one carbon-containing group is attached to the hydroxyl bonded carbon. A vinyl carbon is a carbon atom double bonded to at least one other carbon atom. Vinyl carbons, which are also called alkenyl carbons, are sp2 hybridized. A vinylic alcohol contains a hydroxyl group attached to a vinyl carbon. Note that the vinyl carbon is sp2 hybridized. Can you classify these structures as allylic or vinylic alcohols? Structure A shows a vinylic alcohol. Notice how the hydroxyl group is linked to a carbon participating in a carbon-carbon double bond. Structure B shows an allylic alcohol. The hydroxyl group is bonded to a carbon that is adjacent to a carbon-carbon double bond. Now that we understand the classification of alcohols, let's turn to their nomenclature. The common names of alcohols are derived from the name of the alkyl group with a Y, L ending, plus the word alcohol. For example, the alcohol with the formula CH3OH, shown on the left, is commonly called methyl alcohol. It contains only one carbon, which corresponds to a methyl group. The molecule on the right has a 4-carbon chain in a straight line. This corresponds to N-butyl alcohol, where the N indicates an unbranched carbon chain. In IUPAC nomenclature, the alcohol name is derived from the alkane name of the longest continuous carbon chain. Drop the E from the alkane name and replace with the suffix OL to determine the alcohol name. The location of the hydroxyl group and additional substituents are indicated by using the numbers of the carbon atoms to which these are attached. Let's look at the same molecules we used a little while ago to learn about common names. In the IUPAC system, methyl alcohol with the formula CH3OH is called methanol. N-butyl alcohol is called butan-1-ol. Give the IUPAC names of these structures. Try to find the names on your own before checking the answers. When naming organic compounds, remember to find the longest continuous carbon chain. Start counting the carbons at the end of the chain nearest to the hydroxyl group. In molecule A, the longest continuous chain has 5 carbons. Start counting from the right-hand side of the molecule at the end nearest to the hydroxyl group. Notice that the hydroxyl group is on carbon 2. There is a methyl group at carbon 3. So, the correct name of this molecule is 3-methyl-2-pentanol. In molecule B, the longest continuous chain has 8 carbons. If we start counting carbons at the left end of the chain, closest to the hydroxyl group, we see that the hydroxyl group is on carbon 3 and there is an ethyl group on carbon 4. So the correct name of the molecule B is 4-ethyl-3-octanol. Some alcohols have multiple hydroxyl groups. To name diols and triols, start with the alkane name of the longest continuous carbon chain that contains the hydroxyl groups. The E of the alkane name is retained, and the ending OL is added. The appropriate multiplicative prefixes di, tri, etc. are used to indicate the number of hydroxyl groups present. Numbers in the name then give the locations of the hydroxyl groups. For the example shown here, the longest continuous chain has 5 carbons. We have to start numbering carbons at the right, closest to the hydroxyl groups. Notice that the hydroxyl groups are attached to carbons 2 and 3. So, this molecule is named 2,3-pentane-diol. Alternatively, you may see it written as pentane 2,3-diol. Can you write the IUPAC names of these alcohols? Try to do this on your own before proceeding. Remember to work backwards from the longest continuous carbon chain that contains more than one hydroxyl group. Molecule A has a 4-carbon chain and 2 hydroxyl groups attached to carbon 2. Hence, its IUPAC name is butane 2,2-diol. Molecule B has a 3-carbon chain with 1 hydroxyl group on each carbon. Its IUPAC name is 1,2,3-propane triol, and the common name is glycerol. Molecule C has a carbon backbone containing 6 carbon atoms. Counting from the right, there are hydroxyl groups at carbons 2 and 4, and a methyl group at carbon 5. It is 5-methyl-2,4-hexane diol. Cyclic alcohols are named in a similar manner. Count the number of carbon atoms in the ring. Use the prefix cyclo and the alkane name for the number of carbons in the ring. Drop the E from the alkane name and replace it with the suffix OL. The location of the hydroxyl group on the ring is considered to be carbon 1. Look at the molecule illustrated here. The ring has 5 carbon atoms, so this is cyclopentanol. Practice is essential to mastering organic nomenclature. Can you name these alcohols? Remember that the location of the hydroxyl group is considered to be carbon 1, so start counting there. If there is a choice of numbers, count to get the lower numbers for substituents. So, molecule A contains a 6-member carbon ring with a hydroxyl group and a methyl group. Molecule A is a 2-methyl cyclohexanol, not 6-methyl cyclohexanol. Molecule B contains a 3-member ring with a hydroxyl group and a chlorine substituent. Its correct name is 2-chlorocyclopropanol. Molecule C has a 4-member ring with a hydroxyl group and a bromine atom both attached to the same carbon. Molecule C is a 1-bromocyclobutanol. Let's turn our attention to the class of organic molecules called phenols. Phen is an old name for benzene. So, the benzene containing 1 hydroxyl group is known as phenol. Although the systematic name is benzanol, phenol is an accepted IUPAC name. We can use this as the basis for naming phenol derivatives. Toluene is an important benzene derivative. It has 1 methyl group attached to the aromatic ring. Cresol is the name for toluene molecules that have 1 hydroxyl group in addition to the methyl group. There are actually 3 isomers for cresol. The isomers for cresol can be named as phenol derivatives: 2-methylphenol, 3-methylphenol, and 4-methylphenol. We can also introduce the use of the prefixes ortho, meta, and para to name benzene derivatives. Ortho refers to 1,2-disubstituted benzenes. Similarly, 2-methylphenol, shown on the left, can also be named as orthocresol. Meta is used to refer to 1,3-disubstituted benzenes. So, 3-methylphenol, shown in the center, is also called metacresol. Finally, the prefix para is used for 1,4-disubstituted benzenes. Therefore, 1,4-methylphenol shown on the right is also called paracresol. In IUPAC nomenclature, dihydroxybenzene derivatives are named as diols. Numbers give the locations of the hydroxyl groups. Shown here are 3 examples from left to right. They are benzene 1,2-diol, benzene 1,3-diol, and benzene 1,4-diol. However, the dihydroxybenzene derivatives are actually better known by their common names. Benzene 1,2-diol is known as catechol or pyrocatechol. Benzene 1,3-diol is commonly referred to as resorcinol. Hydroquinone, or just quinol, is the common name for benzene 1,4-diol. Let's do some more practice problems. Give the IUPAC names of the compounds shown here. Remember, the location of the hydroxyl group is carbon number 1. So, molecule A can be named 2,6-dimethylphenol. Its common name is 2,6-xylenol. Molecule B is 4-chlorophenol or parachlorophenol. Molecule C is 1,2,3-benzene triol. It is commonly known as pyrogallo. Ethers are a class of organic molecules that contain a bridging oxygen between 2 carbon-containing groups. The carbon groups may be either aliphatic or aromatic. Ethers can also be thought of as a substituted alkane with an alkoxy or aryl oxy group. Ethers can be classified in several ways. Simple or symmetrical ethers have 2 identical carbon groups on either side of the oxygen. Mixed or unsymmetrical ethers have different carbon groups on either side of the oxygen. The common names of ethers give the names of the alkyl or aryl groups in alphabetical order, followed by the word ether. For example, the common name of the ether shown here is ethyl-methyl ether. If the ether is symmetrical, use the prefix di plus the name of the alkyl group name, add the word ether at the end. The ether shown here has the common name diethyl ether. IUPAC rules for ether nomenclature are based on descriptions of ethers as alkoxy-substituted alkanes. The larger group is considered to be the parent hydrocarbon. A number gives the location of the alkoxy substituent. This makes the IUPAC system more versatile than the common names for ethers. Consider the molecule shown here. It has a methyl group and an ethyl group. The ethyl group contains more carbons. Therefore, the ethyl group is considered to be the parent chain with a methoxy substituent. In the IUPAC system, this ether is named methoxyethane. Here are some problems for you to try. Give the IUPAC names of the compounds shown here. They are all ethers. Remember that the longer chain is considered to be the parent chain. Molecule A is ethoxybenzene. Its common name would be ethyl phenyl ether. Molecule B has a 5-carbon chain with an ether linkage attached to a methyl group at carbon 3. Thus, molecule B is named 3-methoxypentane. Molecule C contains a methyl group and a propyl group. Since the longer chain has 3 carbons, molecule C is named methoxypropane. Its common name would be methyl propyl ether. Molecule D has a 6-carbon substituted alicyclic chain with an ether linkage attached to the ethyl group at carbon 2 as shown. Therefore, its IUPAC name is 2-ethoxy-1,1-dimethyl cyclohexane. Molecule E has a 3-carbon chain with an ether linkage attached to an ethyl group at carbon 2. Its IUPAC name is 2-ethoxypropane. We have figured out the names for many molecules in this module. Now, let's practice going in the other direction. Draw the correct structures for these molecules. Try to work these out on your own before checking the answers. When drawing molecules from names, the parent chain is given last in the name. Remember to work backwards. Molecule 1 is 2,3-diethyl phenol. Start by drawing a phenol ring. The location of the hydroxyl group is position 1 on the ring. Then, add ethyl groups at carbons 2 and 3. Molecule 2 is 2-ethoxybutane. Start with a butane chain which has 4 carbon atoms. At carbon 2, insert an ether linkage to an ethyl group. Molecule 3 is 2-methyl-2-butanol. Start with a 4-carbon chain from butane. Place a hydroxyl group on carbon 2 and then put a methyl group on the same carbon. Molecule 4 is 2-propan-1-ol. Start with a 3-carbon chain since it is a propane derivative. Put a hydroxyl group on carbon 1. The double bond starts with carbon 2. The hydroxyl group outranks the double bond in IUPAC nomenclature. The last molecule is 1,3-cyclohexane-diol. Start with a 6-member ring. Put a hydroxyl group on 1 carbon. That position is carbon number 1. Put a second hydroxyl group on a carbon atom 2 positions away. Let's start by looking at the hydroxyl group in alcohols. The oxygen is sp3 hybridized. It forms a sigma bond with end-to-end overlap with an sp3 hybrid orbital of carbon. In methanol, the carbon-oxygen-hydrogen bond angle is 108.9 degree, slightly less than the tetrahedral bond angle of 109.5 degree due to the repulsion between the lone pairs on the oxygen atom. The carbon-oxygen bond length is 142 picometers, and the oxygen-hydrogen bond length is 96 picometers. Phenol, which is a planar molecule, also has a hydroxyl group, but the oxygen forms a sigma bond with an sp2 hybridized carbon. The carbon-oxygen-hydrogen bond angle is 109 degrees. Notice that the carbon-oxygen bond length in phenol, which is 136 picometers, is slightly shorter than in methanol. The carbon-oxygen bond length is shorter in phenol because the bond has partial double bond character. The lone pairs on oxygen have conjugation with the aromatic ring. Methoxymethane is a typical ether with a bridging oxygen group. The 4 electron pairs around the oxygen, 2 bond pairs and 2 lone pairs have an approximately tetrahedral arrangement. The bond angle of 111.7 degrees is slightly greater than tetrahedral due to the repulsion between the two bulky alkyl groups. Notice that the carbon-oxygen bond length is almost the same as in alcohols. Let's focus our attention on synthetic routes to prepare alcohols. The first method we'll discuss is the preparation of alcohols from alkenes by acid-catalyzed hydration. Here's the general reaction. An alkene reacts with water in acidic conditions to form an alcohol. This method is used less frequently for lab-scale synthesis of alcohols. If the alkene is unsymmetrical, meaning that different groups are attached to the carbons of the double bond, then two possible alcohol products could form. How do we determine which alcohol will be the major product of the reaction? Markovnikov's rule allows us to predict the regioselectivity. The hydrogen will add to the carbon with more hydrogen atoms bonded to it. The hydroxyl group adds to the carbon with fewer hydrogen atoms bonded to it. Let's work through a problem to show the application of Markovnikov's rule in acid-catalyzed hydration of alkenes. Propene reacts with water in a dilute solution of sulfuric acid. What are the two possible products of the reaction? Identify the major product. Start by drawing the structure of propene. Notice that one carbon in the double bond has one hydrogen atom attached, while the other has two. Draw the two possible alcohols that could form. Using Markovnikov's rule, we can determine that the upper product shown is the major product of the reaction, the H atom added to the carbon with more hydrogen atoms. The lower structure is the minor product of the reaction. It's important that you understand the mechanism of acid-catalyzed hydration of alkenes. We'll go through each step in detail. Step 1 involves the formation of a carbocation. The carbon-carbon double bond becomes protonated to form a stable carbocation. Then, water, acting as a nucleophile, attacks the carbocation to form an oxonium ion. Finally, the oxonium ion loses a proton to water, acting as a loose base to form the alcohol. A second synthetic route to prepare alcohols is by the hydroboration oxidation of alkenes. This can be summarized as a two-step process. First, the alkene reacts with diborane to form a trialkyl borane compound. The series of steps that forms the addition product trialkyl borane is shown here. Then, the trialkyl borane is oxidized by hydrogen peroxide in aqueous sodium hydroxide to form the corresponding alcohol. Note that water is not a reactant in the hydroboration oxidation of alkenes. A particularly useful feature of this synthetic route is the resulting anti-Markovnikov's hydration of the alkene. In contrast to acid-catalyzed hydration, hydroboration oxidation results in the hydroxyl group attaching to the carbon with more hydrogen substituents. Let's do a practice problem. Draw the structure of the main organic product formed when 2-methyl-2-butene is reacted with diborane in a suitable solvent, followed by treatment with basic hydrogen peroxide. Start by drawing the structure of the reactant. Since this reaction uses hydroboration oxidation of the alkene, the major product will show anti-Markovnikov's addition. Therefore, the hydroxyl group will attach to the carbon with more hydrogens, as shown here. Another route for the preparation of alcohols is by the reduction of aldehydes and ketones. This involves the addition of hydrogen gas in the presence of a suitable metal catalyst, such as platinum, palladium, or nickel. The overall reaction for the catalytic reduction of an aldehyde to a primary alcohol is shown here. This method also works for the reduction of ketones. Aldehydes and ketones can also be reduced by treating them with reducing agents such as sodium borohydride or lithium aluminium hydride. The overall reduction of a ketone to form a secondary alcohol is shown here. Aldehydes can also be reduced in a similar fashion. Can you answer this question on your own? Give the structure and IUPAC name of the product expected from the catalytic reduction of 2-pentanone. When you draw the correct structure of 2-pentanone, you should immediately recognize it as a ketone, as the carbonyl group is in the middle of the chain. The catalytic reduction of a ketone produces a secondary alcohol. The product is 2-pentanol. Alternatively, you could have used sodium borohydride or lithium aluminium hydride instead of hydrogen gas with a metal catalyst. The fourth route for alcohol preparation involves the reduction of carboxylic acids using lithium aluminium hydride. Carboxylic acids are very difficult to reduce, so this process requires a very strong reducing agent, lithium aluminium hydride. The overall reaction given here shows that carboxylic acids can be reduced to primary alcohols. This is actually a two-step process. First, treatment with lithium aluminium hydride, followed by the reaction with water. Lithium aluminium hydride is actually very expensive, so the use of this reaction is somewhat limited. Since carboxylic acids are so difficult to reduce directly, a fifth synthetic route is used in industrial settings. The carboxylic acid is converted into an ester, which is then reduced. The first step of this process converts the carboxylic acid into an ester. The carboxylic acid is reacted with an alcohol to form an ester molecule and water. Esters are much easier to reduce than carboxylic acids. The ester can be catalytically hydrogenated to form two alcohols. This process requires a specialized catalyst, which is why this process is typically carried out in industrial settings. It's time to try another practice problem. You wish to make a cyclopentyl methanol, shown here, by using lithium aluminium hydride in diethyl ether. Determine the structure of an appropriate starting material. You need to work backwards from the desired product. Remember that using lithium aluminium hydride involves two steps that should be listed over the arrow. An appropriate starting material would be cyclopentane carboxylic acid. Since the desired product is a primary alcohol, you could also start with the appropriate aldehyde instead of the carboxylic acid. Grignard reagents are important in many chemical syntheses. Grignard reagents are alkyl magnesium halides. General formula for a Grignard reagent is RMgX, where R is an alkyl or aryl group. Shown here is methyl magnesium bromide, an example of a Grignard reagent. Grignard reagents provide a sixth route for preparing alcohols. Grignard reagents can be reacted with aldehydes and ketones to make alcohols in a two-step process. The first step involves nucleophilic addition of the Grignard reagent to the carbonyl group to form an alkoxy magnesium halide adduct. Then the adduct is hydrolyzed to form an alcohol. Grignard reagents are useful in preparing a variety of different alcohols. When Grignard reagents are reacted with methanol, commonly known as formaldehyde, the reaction makes a primary alcohol with one more carbon than present in the R group of the Grignard reagent. When a Grignard reagent reacts with an aldehyde other than methanol, the reaction produces a secondary alcohol. The reaction of a Grignard reagent with a ketone produces a tertiary alcohol. Try to answer this question on your own before checking the answer. Give the structure and IUPAC name of the product expected from the reaction of pentanal with ethyl magnesium bromide. Start by drawing the structures of the two reactants. Recall that an aldehyde reacting with a Grignard reagent forms a secondary alcohol. This reaction will form 3-heptanol as shown here. Let's turn our attention to the preparation of phenol. Phenol, also known as carbolic acid, was first isolated from coal tar in the 19th century. Phenol can be synthetically prepared from benzene derivatives. The first route for the preparation of phenol is from haloarenes. In the first step of this process, a haloarene is reacted with sodium hydroxide at high temperature and pressure. In the equation shown here, chlorobenzene is reacted with sodium hydroxide to form sodium phenoxide. Then, the sodium phenoxide is acidified to form phenol. A second synthetic route involves benzene sulfonic acid. This was the first method developed for the preparation of phenol. In the first step of this process, benzene reacts with hot concentrated sulfuric acid, which is sometimes called oleum. In the second part of the process, the benzene sulfonic acid that results is treated with molten sodium hydroxide and subsequently acidified to form phenol. A third synthetic route uses diazonium salts. In the first step of this process, an aromatic primary amine is reacted with nitrous acid from NaNO2 and HCl to form a diazonium salt. Then, the diazonium salt is hydrolyzed with warm water or dilute acid to phenol. The overall equation is shown here. A fourth route to phenol uses cumene or isopropyl benzene. This is the most common industrial synthetic method for phenol. In the first step of this process, cumene is oxidized in air to form cumene hydroperoxide. This is then treated with dilute acid to form a phenol. Acetone is the other product of this reaction.